This is the RCA Videodisc maintenance training film for finishing line 2. First, we will describe the equipment that is on the east side of the pack room wall. This equipment consists of the following: visual inspection, the monorail, the wash tank system, Freon dryer, the oil foggers, and the auto inserter. Visual inspection is located on the far east side of the line as indicated by the red box. This is the speed control for the D-flash stations. A power indicator light is on when the switch is in the on position. There is also a pressure reset and a cartridge fuse device. Normal setting is 80% in the forward mode. The D-flash station control is located directly below the D-flash station. This is an input-output conveyor with a control box located in the lower portion of the picture. There are two types of these conveyors at the visual inspection. This is another type. The spindled product is transferred into the inspection area by these conveyors. Halogen lights are the lighting source for visual inspection. Switches are located on the wall by each door. The visual defect counter at each station are interfaced with the Texas Instruments controllers in the Monorail cabinet. A light goes on and indicates that the input is accepted. The Monorail conveyor system will be reviewed next. This drawing has highlighted the more important aspects of the monorail. This is the monorail control cabinet. A power on indicator is to the right of the emergency stop button. Below is a logic on switch and indicator. To the left of these are the monorail start, stop, and mode switch for either run or jog. Above are indicators for the verify, lube, dry, and wash systems. The inside of the monorail control cabinet houses the Texas Instruments programmable controller for visual inspection. This is located on the right half of the cabinet. The Texas Instruments 5TI controller is used to interface defect information to DMAX. These are input-output modules. They have LED indicators which are on when active I/O takes place. The motor controller and digital readout are on the left side of the panel. There is a one-turn potentiometer below the motor controller for setting motor speed. The monorail conveyor is driven by a 1 horsepower Reliance motor. There is a current limiter in the motor controller. Also, for added protection in case of a jam, there is a shear pin on the main drive unit. This is the automatic take-up, backup, air tank, and regulator. The monorail's automatic take-up is located at the west end of the monorail conveyor, above this backup air tank. If loss of plant air occurs, the backup air will hold the take-up in place till the conveyor is emptied. The regulator should be set at approximately 80 pounds per square inch. Maintenance access to the chain on the monorail is gained through two access points. This access is located between the visual inspection stations and is a side access. The top access point is located above the oil line loading area. These accesses are provided for inspection, repair, or removing a link when the take-up is fully extended. Remove either of the pins to gain access. This drawing shows the layout of the monorail and the location of the control panel, the inspection access, both the side and top access points, the drive unit and motor, the backup pressure tank, and the take-up. Notice that the take-up is at the far west end of the monorail. To see this take-up, walk between the wash tanks and Freon dryer. There is a small ladder that leads to the inspection area for the take-up and tank 3. We will now move on to the wash line. The wash system basically cleans the disc in the Shipley and rinses the disc in the spray booth and wash tanks. The system has high-quality DI water pumped into tank number 3. From there, the water cascades over a weir plate into tank 2 and then tank 1. This ensures that the disc being conveyed out of tank 3 and into the Freon dryer have been rinsed with the cleanest water possible. The wash system is supplied with 2 types of DI water, incoming and polished or treated return water. Heating of all tanks is accomplished through heat exchangers that are supplied with 38 pounds per square inch of steam. The wash system panel has 3 well-defined functions. First, process control. Second, process monitoring. Third, troubleshooting. Process control has 2 modes of operation. The first and normal mode is automatic, which allows the TI-550 programmable controller to control the process. The second mode is manual, which allows for some variation in the selection of switches. The switches being steam, which can be either on or off, and there is a low pressure indicator, Cascade 3, Cascade 2, Cascade 1 pumps, the spray rinse pump, the steam condensate pump, the DI water pump, which is for return water, and the Shipley or chemical pump. Also, we have a process fill. As far as process monitoring, we have resistivity in 3 different locations that monitor the process, monitor the return, and monitor the incoming resistivities. Also monitoring of incoming flow, temperature of Cascade 3, return flow, temperature of Cascade 2, the spray rinse flow and temperature of Cascade 1, and the spray rinse temperature. There is a power on indicator, an emergency stop button, a process go or no go indicator, the auto manual switch which we've discussed, and a start stop. It may be noted that the emergency stop switches do stop the monorail. Besides the panel, there is another emergency stop located on tank 1 next to the spray rinse booth. There is no audio alarm on the wash panel. Rather, there are indicator lights on the main process panel, the monorail cabinet, and this wash panel. If any pump stops or flow, resistivity, or temperature deviate from specification, lights will display the problem. The panel which is most useful for troubleshooting is on the left side of the wash panel. Here is a graphic representation of the process with trouble indicators. The resistivity indicators will be on if resistivity is below 10 megaohms. The temperature of the wash tanks and spray rinse must be in spec, or the direction of the deviation will be indicated. The recirculation pumps in tanks 1, 2, 3, and Shipley, plus the spray rinse pump and return water pump will always be on when the system is up. The chemical add pump will always be off unless adding Shipley manually. The steam condensate pump will only come on for short periods of time in order to transfer accumulated condensate back to the powerhouse. If this light comes on for short periods of time, there is no need for concern. The graphic representation shows the flow of incoming water into the system. At this point, it is where it is mixed with return water and becomes process water. The process water enters tank 3 by the Freon dryer. and cascades around to tank 2, then to tank 1. Spray rinse water is removed from tank 1. The overflow from tank 1 is accumulated for return water. This water is pumped by the return pump. It is pumped through DI polishing columns and then back to the point where it mixed with incoming DI water. Then form processed water. Resistivity for incoming water is indicated at this point, for return water and for processed water. Temperature for tank 3 is indicated, temperature for tank 2, tank 1, and the spray rinse. Pumps for tank 3, tank 2, tank 1, the spray rinse, and the chemical recirculation pumps are indicated there. Indicator for the chemical add or Shipley add pump is on the top right. This is the inside of the wash line panel. To the top right, we have the main power breaker. Fuses and relays for the pump motors take up most of the wash panel's right side. To the bottom right, we have 2 transformers. The back of the door houses the display monitors. Various switches for the control of the wash line. And the resistivity meter and its switch, as pictured here. The wash system has an auto start feature whose control is on the right side of the panel as seen here. The left-hand side of the wash panel houses the programmable controller and its components. To the top left of the panel, we have the DC power supply. And to the right of that, we have the TI 550 programmable controller. Here we have 7 MT analog input modules. To the left of that, analog thermocouple modules. This is a loop access module for the TI. And here are the various input-output modules. This transducer or pneumatic panel is located on the back of the wash panel. This series of regulators and control components control the solenoid air, heat of the spray rinse, wash tanks, 321, and incoming process heat. This panel is controlled by the TI-550 programmable controller, which is tied into thermocouple sensors and flow meters throughout the system. Regulators throughout the panel control the amount of instrument air a valve receives. When a sensor varies from a range which has been preset, the TI sends a signal to either a transducer for steam control or a solenoid for water valve control. Color-coded tubing for the system air is a convenient tool for troubleshooting. Each individual system of heat control has one regulator for main input air, a second regulator for the bypass control in case the transducer were to fail. Here we have the main regulator and its gauge, the bypass system, valves, and gauge and regulator, the automatic line, which is the transducer, its valves, a gauge, and another shut-off valve. Normally, if you were going to run this in bypass, you would shut this valve and the other valve in front of the transducer. You would then open the bypass valves and regulator and adjust the regulator to correspond with the amount of heat you wanted to the heat exchanger. This regulator controls the amount of air going to the process water valve. This solenoid controls the main steam valve. This solenoid B controls the process fill valve, and solenoid A the rapid fill valve. All of these valves are located under tank 3. This is a view of tank 3 looking north. This is the south side of tank 3 with all stainless steel panels removed. Access to tank 3 is by removing the stainless steel panels, or there is an access point between the main wash tanks and the Freon dryer. Underneath tank 3 is a variety of components. We have steam, DI water, plant air, instrument air, steam valves, water valves, main filters, filters tank 3, chart recorder, and recirculating pumps. We have DI sensors, flow meters, steam sensors, thermocouples, main heat exchanger, return heat exchanger, tank 3 heat exchanger, and a DI return flow control and DI return regulator. This is a DI sensor inserted into the stainless steel pipe. These sensors can be damaged very easily, so caution should be taken. Here are the two steam valves that control heat to the main heat exchanger. These are the two smaller blue valves that are in the foreground. In the background we have a blue valve, and there is another one directly behind that that control the main process fill and rapid fill for DI water. This is the steam pressure sensor. Normally steam pressure is about 38 pounds per square inch. If steam pressure drops below 36 pounds per square inch, the light by steam low on the main panel will come on. Access to most of these components is relatively easy, but in certain cases removal or repair is difficult. Underneath we have the main incoming water line after it has been mixed with the return line, and it goes through two main filters, which are the tall silver canisters you see. Each filter system on this system has a bypass. This allows removal of filters while operation continues. Behind this is the main heat exchanger. Each individual tank system has a recirculating system. We are looking at Tank 3's recirculation system. This site flow meter is one of many throughout the system. By the filtration system of each circulation system, there are pressure gauges to determine when the filter should be changed. And as mentioned earlier, there are bypasses on this system. Recirculation is obtained through a teal pump. The pump is supplied from water at the base of Tank 3. Covers for the system are all individually numbered, both their location and the stainless steel cover itself. There are inserts on the framework in order to install the covers properly. There are no screws to these covers. You just match up the covers in number, lift in place on the framework. It may be noted that these stainless steel covers do have some sharp edges. The ends of every cover have a place which has been ground and is very sharp. The front of the line, which we are seeing now, in the foreground is the north side of Tank 3. Then you get to Tank 2, Tank 1, and at the very far end is the Shipley. The tanks themselves, as seen by this drawing, you see the Shipley, you see the spray rinse booth, tanks 1, 2, and 3. All tanks have recirculation systems and filtration systems. Tanks 1, 2, 3, and spray rinse have heat exchangers, thermocouples, 2, one for temperature control and one for temperature monitoring. This double thermocouple system ensures proper control and temperature of the tanks. Here we have the DI recirculation system. First, number 1, the reservoir. Number 2, the recirculating pump. Number 3, the flow control. Number 4, reheat and cool exchanger. Number 6, the DI tanks, or the DI columns. And number 5, the pressure regulator, which mixes the water from the return system with the water from the incoming system to form the process water. At number 1, the reservoir, or the accumulator for the return pump, DI resistivity is approximately 2 mega ohms. After the water has been pumped through the DI columns, the resistivity has increased to 15 mega ohms. System specification is 10 mega ohms minimum. Here we see the location of the facilities entering the area. This is directly above the Freon and wash line. Next we will discuss the Freon dryer. We notice we have the Freon dryer, the still, accumulators, water separators, and the main panel. Familiarize yourself with these components. Facilities supplying the Freon dryer are chilled water, steam, water makeup, and instrument air. In the Freon dryer, what occurs are disc being sprayed with Freon. You have Freon evaporation, Freon condensation. The Freon dryer supplies the still with Freon and supplies water separators with Freon and water. We will go into detail on the various aspects of how Freon moves through the system and the components associated with that. The still also has Freon processing, Freon evaporation, and Freon condensation. And the still supplies accumulators and supplies the water separator with Freon and water. The accumulator is specifically for Freon collection, and this collection is to supply the dryer with Freon. Water separators do several things. They collect the water and Freon by gravity. They separate Freon from the water, and they gravity feed Freon back to the dryer and to accumulators. The water itself that is separated from the Freon overflows into the trench and then to the drain. This is the main Freon panel, and in design is very similar with the wash panel in layout. At the top right, we have power on indicator. To the left of that, an emergency stop button. This emergency stop button will also shut down the monorail along with the Freon dryer. To the left of that, we have process go, process no go, and vapor up. Below that, we have the distillate spray temperature and the distillate spray flow. Directly below that are control switches, the steam on-off and its indicator, dryer heat on-off and its indicator, still heat on-off, its indicator, the steam condensate pump on-off, still transfer pump, which is auto, off, or manual, here indicated by hand, hot water pump, distillate spray pump, and the storage pump. Notice that the storage pump is permanently locked out. This is to ensure that the pump will not accidentally be pushed on. The pump is only used when emptying the Freon dryer. To the left of the main panel is the Freon troubleshooting panel. The panel itself has graphics as in the Wash Lube troubleshooting panel and indicators. They function in very much the same way. We have a hot water pump indicator, water makeup indicator, still transfer pump indicator. We have sensors for the vapor, high temperature, liquid low or liquid high level for the still. Also the storage pump light, and the steam condensate pump, which is very similar to the steam condensate pump on the wash line. In the Freon dryer itself, we have a high temperature indicator, liquid low level indicator, vapor high indicator, and the distillate spray pump indicator. The steam condensate pump will cycle on and off, and as long as this light does go off, there is no need for concern. There is a self-test function on each of these indicators. Just push and they will light. The layout of the panel assists in troubleshooting of the system. This is the inside of the left portion of the main panel. It's called the Freon diagnostic panel, and here we have the indicators, terminal strips, and the wiring. Relays, fuses, motor starters. Here we have the right-hand side of the panel. Which is called the Freon control panel. Here we have analogic digital set points for both the Freon flow and the Freon temperature. A light will indicate when either temperature or flow has gone out of specification, and the reset button on these set points can be reset. On the inside of the right side of the panel, basically all there is the main on-off breaker and one terminal strip. The Freon facilities are supplied from directly above the Freon dryer and wash line. There are various shutoffs above the ceiling at this point. The main steam line runs down the still and around the Freon dryer's south end, and around to the west end, where we have a bypass system along with an automatic system. The steam then underneath the still enters a heat exchanger, which provides heat for the heating recirculation. Here we see the hot water pump for circulation. It is the closest pump to us. The hot water circulation system provides heat to both the Freon dryer and the still. The condensate from the heat exchanger, gravity feeds over to this accumulator, which accumulates the condensate and pumps it back to the powerhouse for reuse. The heating supply itself, after leaving the pump, is piped over to the west end of the still. There is a solenoid valve and plumbing systems for either the dryer or the still. This is why we saw a switch on the main Freon panel for still heat or Freon heat. There is also pressure gauge and temperature gauge at this point. The still heating supply provides heat to the bottom two coils on the inside of the still. The hot water from these coils heat the Freon to its boiling point. 140-degree water can boil Freon because the boiling point of Freon is 117 degrees. And you see on this gauge, the hot water supply return is 140 degrees. After the water leaves the still, it can be considered heating return, since it will travel back to the main heat exchanger to be reheated. The dryer is very similar to the still in that it also has heating coils at the base of the dryer. Chilled water is supplied to the system in order to condense the Freon after it is heated. Here, these black insulated pipes are the chilled water. Below that, you see 3 dials which indicate the return temperature of the chilled water. Cooling coils are both in the Freon dryer and the still. Here we see a representation of what actually occurs in both the dryer and still. We have chilled water and we have steam that changes into hot water. Basically, the hot water boils the Freon evaporates and then cools and condenses on the cooling coils where there are troughs to collect it. The Freon is collected and then travels to a water separator. Here you see a separator and the Freon gravity feeding out to the accumulator. The accumulator supplies the main spray pump, which is at the base of the photograph. The Freon is fed past the flow meter, past the thermocouple, into a heat exchanger, which reheats the Freon to approximately 110 to 115 degrees. Freon is then sprayed into the Freon dryer on the disc. In the dryer itself, as you see in this graphic, you have a still transfer pump, Freon spray pump. You see the dryer, the still. The S's indicate water separators, the A indicates accumulator. The Freon is pumped in the dryer from a drum. It is transferred to the still from the dryer by the still transfer pump. Freon from the dryer and still gravity feed into separators. Separators gravity feed the dryer and the accumulator. There, from the accumulator, the spray pump feeds the dryer. A graphic representation of what actually occurs with the Freon is indicated here. We see the drum, which supplies the Freon to the dryer by a pump. Any pumping on this graphic is shown in red, and any gravity feed is shown in black. From the dryer, we can pump it to the still, or we can gravity feed to a separator. From the still, we gravity feed to separators. From the separators, we can gravity feed to the accumulator or gravity feed back to the dryer. From the accumulator, we spray or we pump the Freon back to the dryer. Excess Freon is given off as gas in the dryer and is collected by the Freon collector. Here is the still transfer pump. This pump transfers Freon from the Freon dryer to the still. There are level controls in the still, and this pump comes on when Freon is needed in the still. The float controls are on this end of the Freon still. On the still are various sensors in order to keep the system in control. Here we have high vapor level, high temperature, high liquid level, or low liquid level. These indicators are very similar to the ones that are on the dryer. Here is a high vapor control on the dryer. There is a reset button on the top of this temperature controller. There is a dial indicator as seen here on the inside for set point. When the temperature exceeds the set point, a switch is set and the light will light for vapor high. This is the high temperature controller. It is identical with the vapor controller. What determines the difference between the two is actually the location of the thermocouple and the set point on the dial indicator. If a trouble light should light for either of these sensors, first thing that should be done is the sensors should be reset. On the still, you have the exact same sensors, and they are on the south end of the still, approximately 7.5 to 8 feet high. On the dryer, we also have a vapor up indicator, which is located on the main panel. The sensor itself is on the south end of the Freon dryer and is basically identical to the sensors that are for temperature high and vapor high. The sensor is located directly behind this heat exchanger. The Freon gas, which we discussed earlier, is collected through these ventilation systems on both ends of the Freon dryer. It is vented over into carbon filtration beds in the north boiler room. The storage pump and its stop switch, as indicated here, is on the Freon dryer panel and is permanently locked out. If it is needed to be used, pull this lockout out of the way, turn the storage pump on. This is a remote location of that storage pump switch. All the Freon in the dryer will be pumped over to a main storage tank near line 1. The storage pump itself is located directly behind this main recirculation heating pump. In review of the Freon dryer and its systems, we again have the Freon dryer, the still, the accumulator, and water separators, and the main Freon panel. The oil line will be our next topic. Here we see a layout of the line with some of the main items of interest. Starting with the right of the screen, the east end of the oil line, we see the conveyor take-up. F1C1 represent fogger number 1, compressor number 1. Between the fog chambers we have the four-arm turnover, and to the north of the turnover is the mist collector. Next, fogger number 2, compressor number 2, and the far west end is the two-arm turnover. The main panel is south of the lube line. On this drawing, we see the location of the real-time aerosol monitors, or RAM, the oil drain pots, and to the far west end, the DC motor and air-operated clutch. This drive runs both turnovers and the oil line conveyor, along with the auto inserter's transfer arms. The facilities which supply the oil line are chilled water for Mocon heaters, plant air for the rams and the conveyor emergency stop and clutch, also plant vacuum which supplies the auto inserter with vacuum.
Lube process. Warning lights are on the north side of the electronics enclosure. Each light is on to represent a condition which is out of normal limits. A flashing light is a process failure, and in auto mode will shut down the process. The title at the top of each light gives you a general location of your discrepancy. In the upper left of your picture are two sets of thumbwheel switches, which are used to set up the high and low limits for both fog chamber oil baths. AC distribution and fusing is done from the west part of the electronics enclosure. On the east side of the electronics enclosure is a Texas Instrument controller, controller input-output modules, and analog modules. Please note, service of these devices should be done by someone who has formal training in Texas Instrument controllers. The small black box lower right translate takt pulses from conveyor motor to 4 to 20 milliamp for the Texas Instrument controller. In the center of the enclosure is a device known as a TCAM and is used to enter process limits by authorized persons only. Details provided by Disk Engineering. Also at the top of the panel is an AC transformer and line conditioner. Here we see the conveyor speed control, motor driver, board. Please note, readout is in discs per hour, not RPM. To its right, we see the compressor, controllers, and driver boards. Note labels above each one. On the south side of the lube line, centered on each chamber, is a RAM, real-time aerosol monitor, and 9 warning lights. Each light is labeled to the system it designates. Red is an emergency, yellow solid is a warning, and yellow flashing is a process failure. The testing of these lights can be accomplished by pressing each light individually or by using the lamp test button on the lower right-hand corner. Each oiling chamber is equipped with a RAM. The RAM measures the fog density going into the nozzle on a scale of 0 to 20. Note, the RAM is calibrated at the factory. Behind each RAM and below the particular fog chamber, there are RAM dilution chamber and metering equipment, which consists of motor drive, sampling pump, air regulators, shutoff valves, airflow indicators, and an infrared detection system. At the bottom of your picture, we see the main inlet air control valves. Dual regulators, one for sampling and one for dilution. Two airflow indicators. The one on the right is for dilution, on the left for sampling. A Bodine motor is used to drive a sample pump which draws the sample from the tube. Note the drive system has a motor controller which is set at 80 RPMs in the reverse direction. The sample pump is a veritable type which is set at 0.4 centimeters per revolution. The dilution chamber has a sample shutoff valve at the top of your picture. The sample comes in through the tube at the top, and the dilution air comes in from the left, is mixed on a standard 1/4 inch T, and is diluted in the chamber. The sample drawn out of the chamber through the infrared detector by the use of an aspirator. This completes the RAM, Real-Time Aerosol Monitor System. There is a glass window on the side of each fog chamber, which you can use to note debris and the amount of fog in the station. Between each fog chamber, there is an emergency shutoff switch, large red button, left-hand side of the picture. There are also system lights. Remember, yellow solid is first warning, flashing is a system shutdown. Note the test switch on the lower right-hand side. Above we have the 4-arm turnover station, which is now feeding into chamber number 2.
Here we have a diagram which basically shows the fogging system. The reservoir is filled with fraction 1 oil. The oil pumps oil into the aerator where the oil level is controlled by a weir plate. The MOCON controls the oil temperature by heating or cooling an exchanger which is built into the aerator. The compressor forces clean air at approximately 2.5 to 3 psi through small tubes under the oil surface in the aerator. This compressed air causes bubbles or fog. The fog, because of least pressure, moves out of the aerator through a tube to the top of the fog chamber and out the nozzle. The intake of the compressor completes the loop. The compressor removes fog and air from the chamber to the muffler. The muffler removes some oil from the fog and the cycle begins again. We will review the various components associated with this diagram. Here we have the oil pump and motor. It is a Zenith metering pump. It's housed underneath this cover and is a positive displacement pump. The oil is pumped through a filter which has a bypass system into the aerator chamber below the filters. We see the reservoir. The reservoir is supplied by overflow of the aerator chamber over the weir plate. This is also where oil is filled. This panel houses the motor controller for the Zenith pump. The thumb wheel setting is normally set at 20 RPM. Here we see the MoCon. The MoCon controls the temperature of the oil through a heat exchanger that is connected to the aerator. The MoCon itself heats water and also has chilled water supplied to it for cooling the chamber. Here we see the bottom of the aerator chamber where the MoCon lines go into the exchanger. The MoCon has a dial temperature controller. Here we see the housing over the compressor and the compressor motor. The motor runs at approximately 3,300 RPM. The compressor forces 2.5 to 3 psi into the aerator chamber. And into the small tubes that are underneath the oil surface. There is a valve for regulating the pressure, and also the motor speed can regulate the pressure. Here we see the top of the aerator chamber and where the fog exits the aerator chamber into the tubing. We see the tubing goes down to the surface of the fog chamber. The nozzle attaches to the inside of the fog chamber to this tubing. Besides the intake for the muffler, we have an exhaust which goes to the mist collector. The exhaust is full of oil, travels down some tubing to the mist collector, which we see here, and we also see the oil pots at which the excess oil is drained into. Here's another view of some of the exhaust system, which travels to the front of the mist collector here. We see the mufflers on either side of the compressors, which also have oil pots connected to them, which drain off excess oil. After the oil has been filtered and drained out, the exhaust exits through a ventilation tubing past a switch which detects the flow. The ventilation tubing also is connected to the main booths themselves to vent of any mist or fog that is excess. There is a switch which detects the fan's ventilation system, whether it is on or off, and this is on the roof. Here we see the ventilation system which is connected to the booths. Here we see the forearm turnover. The turnover is driven by the main conveyor chain through a sprocket. The sprocket is underneath the chain at this point on the conveyor. The forearm turnover is driven by a timing belt which is connected to the sprocket. Here we see the location of the take-up on those timing belts. This is the main conveyor take-up, which is located on the east end of the conveyor. It is important that the conveyor chain is kept even and the take-up is even. Otherwise, the forearm turnover can get off track due to an uneven chain. The oil line operator has two emergency stops on either side of the load area. Here we see the motor, the clutch, and the drive. The location of this is on the far west end of the conveyor. Access to the bottom of the chain is easily obtained underneath the conveyor, as we see here. When doing maintenance on the fog boost, removing the glass doors is accomplished easily. Also, panels are removed from the bottom of the line easily and are notched for positioning. Here we will review the mist collector, the compressors, the turnover, the fog stations 1 and 2, and the take-up locations. Here we see the oil drain pots, Ram 1, Ram 2, the drive, clutch, and motor system, the electrical panel, and again the location of the take-up. Here we see the facilities that are supplied to the oil line, the chilled water, the plant vacuum, plant air. Next we have the auto inserter, which is at the far west end of the oil line. Main points of interest here are the main electrical panel, the operator panels, which are on side 1 and side 2, and the output conveyor, which transfers product from the auto inserter into the pack room. Here we see the location of the disc verifiers, which verify the barcode on the disc, and the caddy barcode readers, which verify the barcode on the caddy. Here we see the magazines for caddies and spines. The spine magazine holds 100 spines and the caddy magazine holds 50 caddies. The magazines are loaded at the location where it says spine in and caddy in, and the empty magazines are ejected where it says magazine out. The disc transfer is illustrated here. We see the disc conveyor on the oil line, the 2-arm turnover, the 2-arm transfer, and the 3-arm rotating transfers. All of these transfer systems are driven by the oil line conveyor motor. It is important that we realize these systems are interconnected. Here we see the spine transfer. The spines are transferred from the magazine to a rotate station, which orientates them correctly, down a walking beam to the insertion station. The caddy transfer The caddies are transferred from the magazine to the walking beam, which transfers the caddies down to the insertion station. The caddy, spine, and disc are assembled at the insertion station. The parts are conveyed by the walking beam to the output station. Side number 2's output station has a rotator which orientates the assembled part to side number 1. The assembled part is conveyed to the output conveyor by a small transfer conveyor. Here we see the disc on the oil line being conveyed through the fogger and on to the auto inserter. Here we see a view of the transfer systems. The parts are picked up by the two-arm turnover, which deposits them on a pedestal, which is picked up by the two-arm transfer, which then deposits them on a verifier. The discs are then transferred from the verifier to a reject station by the three-arm turnover, then to the insertion station. From the insertion station, the assembled part is conveyed down the walking beam to the output station. This is side number 2, which has the rotator. The parts are then conveyed to the pack room by the output conveyor, which we see here. Here we see the operator station and the caddy and spine magazine feed conveyors. The operator's panel is laid out and easily marked for identification of the switches. The start button is in the top left-hand portion of the operator's panel and displays a green light when lit. The verifier off button directly below the green start button. Here we see the disc conveyor stop, and below that an emergency stop which stops both the verifier and the conveyor. Here we see the auto or manual cycle switch and the reset display switch, which resets the alphanumeric display that we see here. This is the Burr-Brown terminal, which connects to the verifiers. Spine elevator bypass or auto switch. Normally in the auto positions as the caddy elevator bypass auto switch is. Spine elevator switch. Caddy elevator switch and load spine index. caddy index. Disc verify or spindle mode switch. The spindle switch automatically spindles any disc coming down the conveyor. The operator panel is very self-explanatory. Turn the cycle switch to manual in order to execute any of the functions that are desired. Here we see magazines on their appropriate conveyors and the position at which they are loaded. Please note the magazines being loaded on the right-hand side of the screen. It's a matter of lining up the carts and pushing the magazines into their appropriate conveyor. Here we see the conveyor for empty magazines. The empty magazines trip a sensor, and when the sensor is tripped, the magazines come out the conveyor onto the track. The transfer of the disc from the oil line conveyor occurs with the two-arm turnover. Here we see the cam action of the two-arm turnover as it picks up and releases the disc on the pedestal. Here we see the pedestal and the two-arm transfer and the release from the two-arm turnover. Here is the three-arm transfer that picks the disc up from the verifier, brings it past the reject station and over to the insertion station. The spine magazine must have their spines alternately stacked in order to be stacked straight. It is important that the spine stacks are stacked straight in order for the elevators to lift the stack up off the magazine and correctly feed the spines onto the walking beam and the rotate station. Note that the rotate station is orientating the spine to the proper direction. Here we see the spine fingers for pushing the spine from the rotate station to the walking beam. And we see the fingers picking the spine from the stack, placing it on the rotate station, here we see the spines being conveyed down the walking beam to the insertion station. Here we see the caddy stack and the feed station. The caddy is being removed to the walking beam. We'll see a new stack come up in just a second. Feed into position right now. And without missing a caddy, we feed the next caddy onto the walking beam. And we see the caddies moving down the walking beams to the insertion station. Note also optical sensor and the barcode reader. Here we see the insertion station and the pusher to push the caddies into the disc and spine. The walking beam then takes the part after it has been inserted and conveys it down the conveyor to the output station. Here we see another angle of the pusher. This is where the caddy, spine, and disc all get assembled. Here we see the output conveyor and the output optical sensor. This sensor is so that if the conveyor backs up, the disc gets spindled on the inserter automatically. Once again, we'll review the entire process. The disc come down the wash line to the 2-arm turnover. From there, the 2-arm transfers the disc to either of the verifiers. And from the verifier, we transfer to a reject station, and from the reject station to the insertion station. Then down the walking beam to the output station, where we have the output conveyor, right here, and into the pack room. This graph represents
the electronic communications between the verifier, blue, center picture, burr brown, upper left, laser scan barcode reader, violet, upper right, and the Texas Instrument 550 controller, orange, center right. The disk verifier uses an Intel computer to manage the information from the barcode reader for the caddy and a disk camera reader for the disk. This information is compared for a match or mismatch signal, which is then fed to the TI. The TI is either going to instruct for rejection of the disk and caddy or insertion of the disk caddy pair. The burr brown is used for mode and tack on information to the Intel and or disk verifier. Please note, the burr brown also has the capability of putting the Intel in a bypass condition, which sends a signal to the TI of this bypass, which means that insertion will take place whether match or mismatch has occurred. Please note that all other protections are still invoked at this time.
Here we see the reject station where discs are deposited if verification has not taken place or if spindle all disk switch is set or if the disk inserter jams. The 2-arm turnover can have various problems associated with it. If the cams are out of sync, if the vacuum on the opposite pedestal has not enough vacuum, if you have a wreck, or if certain adjustments are out of adjustment. The cams control the pickup and placement of the disc from the conveyor to the pedestal. The vacuum is there to steady the disc when it is placed on the pedestal. If you have a wreck, the timing belt, the cams, or the location of the pickups themselves may need adjusted. Certain adjustments which could cause a problem are the reference from the conveyor to the auto inserter, and this reference can change if a wreck on the oil line occurs. Here we see the two-arm turnover, picking up the disc from the conveyor to the pedestal. Note how the pedestal steadies the disc without it moving or varying. This is because of the vacuum. Notice how the arms, as they enter the cam slots and exit the cam slots, pick up or place the disc. The transfer arms, the fingers have adjustments to them. There are actuators that can be adjusted, and the timing of them can be adjusted. Normally the fingers are in a position which is all the way down. They can miss disc if this is not occurring. The actuators determine when the disc is going to be picked up and placed. As you see here, the two-arm transfer and the three-arm transfers pick up the disc and actuate the fingers at the same time. Here we see the three-arm transfer. Note that the white fingers are in their lowermost position. Caddy and spine feed. First we have the parts, or the caddy and spine, the stacking of the magazines, the sensors, the photo and proximity sensors, the walking beam, the feed and release of. The caddy and spine parts themselves have to be straight and stacked properly on the magazine. Photo cells and proximity switchers can get out of adjustment, and these can cause wrecks if out of adjustment. The walking beam feed and release also can cause problems if their adjustments for feeding or releasing get out of adjustment. The spine presents additional problems in that it must be rotated, and if the parts themselves are not properly orientated, you can jam at the rotate station and at the spine feed station. This is where the stacking of the spine becomes very important. Most of the adjustments on the caddy and spine feed mechanisms are very precise. An adjustment of 1/4 of an inch is very critical. Here we see the spine, feed, and magazine feeding into position, and the walking beam and the pickup removing it to the rotate station. Note that the rotate station rotates 180 degrees. Here we see the caddy feed from the top of the caddy stack onto the walking beam. The caddy is indexed each time the machine cycles, and here we see a new stack coming up into place. Since the caddy is 1/4 of an inch thick, this is why critical and precise adjustments are necessary. Here we see both walking beams and the insertion station. The alignment of the spine and the disc and the positioning of the caddy prior to insertion is another critical adjustment. There is a vacuum on the back side of the video disc in the bead area that is required to keep the disc in the spine during insertion. Here, the insertion station itself, we have stops for both the caddy and the spine. We have sensors that determine if everything is ready prior to insertion. We can have problems with the parts for both the spine, disc, and caddy, and the feed and release mechanisms that insert and then index the caddy, spine, and disc. It may be noted that the sensors play a critical part in the insertion station. We have a sensor that senses the disc on the verifier, a sensor that senses the disc at the insertion station, a sensor that senses the disc on the spine walking beam and at the insertion station, and a caddy sensor. Here we see the insertion and the output end of the walking beam. It may be noted that interference with the 3-arm transfer or the inserter arm cannot occur. They physically cannot touch each other. Here we see the disc being precisely placed inside the spine and the caddy moving into position, inserting the caddy, disc, and spine together. Note the chrome placement arms, which guide the disc into the spine. In review of the auto inserter, main points, please note the operator panels, the main panel, and the output conveyor. The switches on the operator panel should be set in manual in order to test the machine. The position of magazines, elevator arms, transfer arms, and parts will depend on whether certain switches for testing can be used. The elevator flights must be in the loading position in order to eject a magazine. The spine walking beam cannot be indexed if the caddy walking beam is not in its home position. The spine walking beam cannot be indexed if the transfer arms are not out of the way of the walking beam. Spine transfer cannot take place if a spine is at the insertion station. This is a caution. If the conveyor jams on the lube line, do not restart the conveyor. Inspect the conveyor's chain, the timing belts, the 3-arm transfers, the 2-arm transfers, and the turnovers. Start only in a slow speed, approximately 200 discs per hour. Utilize the clutch stop that is at the turnovers in order to verify or check the conveyor. It is best to restart this with another person present in order to take a look at the entire line. What this film has gone over is the wash lube pack line. The front portion of the line, visual inspection, the monorail, the wash line, Freon dryer, oil foggers, and auto inserter. Questions regarding this film can be directed to manufacturing engineering. We suggest that you take some time to take a look at each of the equipment that have been reviewed in this film. write down any questions you do have so we can review them with you. This concludes the front portion of the Wash Lube Pack film and training tape.